Okay, so in this video I'm going to go through some SAC revision questions. I'm probably not going to go through all of them, but I'll certainly go through enough to so you can set of questions which you can work your way through. Okay, so let's start from question one. What is the voltage across the 60 ohm resistor? Now, it's imperative that you know how to use Ohm's law around a circuit. So let me just get my pen. Okay, so the voltage, what is the voltage across the 60 ohm resistor? So we want to know what the voltage across here is. So we'll call that B 60 ohm. So we're trying to find what that is. In order to do that though, we need to know what the current is. So the current is equal to V on R, which is equal to 120. Now, no, let's have the total resistance, not the resistance of that resistor. So we're trying, the total resistance is 9. So we've got 1.33 amps for the current. So if we want to find the voltage across that 60 ohm resistor, then we can use Ohm's law. Is the current across the 60 ohm resistor. Now the current is going to be the same because it's going to come around here. The current through here is going to be the same as the current through here in a series circuit. So we've got 1.33 times 60, which is 80 volts. One mark for the working, one mark for the answer. What is the current through the 30 ohm resistor? We'll just work that out. And that's 1.33 amps. The circuit is assembled with 3 resistors and a DC power shown as to the right. What is the effective resistance of 3 resistors in the circuit? So we've got a resistor, so the effective resistance is equal to the 400 ohms. Now, in parallel, we've got 1 over 300 plus 1 over 600 to the power of -1. Let's do that in calculator. 1 over 300 plus 1 over 600 is going to be 200, so that's going to be 400 plus 200 is 600 ohms. Now we know the effective resistance is 600 ohms, so we can use that to find out the current. So the current is equal to the voltage, which is 6 over 600, which means it's going to be 1 over 100, which is going to be 0.1 milliamp. 0.01. Sorry, 10 milliamps, which is 0.01 amps. So the voltage, so we've got 0.1 amps goes through here, and then we're going to have the current split off. More current's going to go through less resistance through here. So we know that the resistance, we're going to have double the currents going through this resistor. Where's this one? What is the voltage across the 600 ohm resistor? Well, in order to do that, we need to work out what the voltage drop would be across here. So the voltage drop across the 400 ohm resistor, this is how I would do it anyway, is equal to the current, which is 1.33 times 400 ohms, which is equal to 80 Okay, so I'm going to really trying to rush here, so I just paused it. So the current actually is 0.1 amps, we just worked that out before. So that's times 0.01, which means the voltage across the 400 ohm resistor is 4 volts. Now, if we have a 4 volt drop across here, and we've got 6 volts coming from the supply, assuming no internal resistance, we know that there's going to be, for each of these components here, there's going to be a 2 volt drop, because they're in parallel, they're both going to receive the same voltage. So the 2 volt drop across there. So now that we know that what the 2 volt drop across there, we can then work out what the current is. So the current of the 300 ohm resistor is equal to the voltage of the 300 ohm resistor divided by the resistance. So the voltage across the 300 ohm resistor is 2 volts and the resistance is 300. Doing that in the calculator, we get 6.66 milliamps. Six point six milliamps. So there we have it. So naturally, if we've got 10 milliamps coming through here, and we've got 6.66 milliamps going this way, then we're going to have 3.34 approximately milliamps going this way. Current in, current out. Kirchhoff's current law. Okay, let's continue. With this question, I'm just going to have to read through it first. If the like load B breaks, how will this affect the remaining like load? So let's have a look at the graph. So if this breaks, then what will happen is that breaks the circuit here. There's no way that electricity is going to go through here. If the fuse breaks, then there's no longer enough electricity. So it's going to be electricity this way. So let's have a look through here. There's going to, we're assuming that they're exactly the same, this globe is going to receive 6 volts, assuming they're the same, and this is going to receive 6 volts. So in this arrangement, so both like globes receive 6 volts. So they will be fine. Now, let's have a look at question 5. They were looking at this arrangement here. If globe F breaks, how will this affect the arrangement? Well, if globe F breaks, then first of all, we know that the resistance here is going to be half that of the resistance up here. So if that's half of the resistance up here, then what's going to happen is I'm going to make the assumption that we should know that there'll be an 8 volt drop across there and a 4 volt drop across here, because no longer do we have a parallel circuit for this section here. For section 1, it's just going to be a resistor in series, and that's in series with 2 in parallel. So there's going to be 8 volt drop across the top, 4 volt drop across the bottom. So if globe F was to break, then globe E will blow. This will break the circuit, and so therefore no globes no globes will light up. The only way in this arrangement will work again is if globe F and then E were replaced. Okay, so because then they'll each receive 6 volts, which is perfectly fine. Alright, let's go to the next question. Draw a circuit that has a 50 ohm resistor connected in series with a 100 ohm resistor. So let's have a look. So we've got 12 volt supply. So we've got a 100 ohm resistor in series with a 200 ohm, 50 ohm resistor. Okay. 100 ohm resistor is connected to a voltmeter to measure the voltage across it. So we'll call that V1. The 50 ohm resistor is connected to an ammeter measuring the current flowing through it. So I guess you could have an ammeter there. Alright, so that's fairly straightforward. Have a look at this one. The circuit diagram on the right, 2 identical globes that are connected in series. Okay, so currently the switch is open. With the switch in the open position, describe the relative intensities of the 2 light globes. So electricity is going to flow through here, here. They're both in series, they're both the same. They'll both have the same intensity. Because they both have the same resistance, they'll both be the same voltage drop. Describe any changes to the circuit and the reasons for the changes when the switch is closed. Well, when the switch is closed, globe A will work due to switch creating a short circuit. Okay, I'm flying through these, but I don't want this video to go for too long. You can always stop and replay. We've got a generator over here, and we need to use the information above to calculate the following. What is the current in the transmission lines? Now let's have a look at how a transformer works. Basically, a transformer has so many coils, and we have a ratio of coils from, I guess this might be, there's 1 coil for every 5 coils. Okay, so let's just say if we had 50 coils on the left, then we'd have to have 250 coils on the right. And what that will do is it will step the voltage up or down, depending on whether it's 1 to 5 or 5 to 1. 1 to 5 is going to step the voltage up. So let's have one thing about an ideal transformer is that the power in is equal to the power out. Now, if we've got 250 volts going through a transformer, and it's going to step the voltage up by a factor of 5. So the voltage in is going to be 250 volts coming through here. Therefore, it's going to be stepped up by a factor of 5. So there's going to be 1,250 volts here, but it has the same power as before. So the power in is equal to 1,000. It's equal to the power out, which is equal to V times I, P equals V times I, which is equal to 1,250 times the current. So, From before, we could work out what the current is as well. The current is 250 times the current is going to give 1,000. So the current coming through here is 4 amps. But the current coming through the transmission line the voltage has been stepped up by a factor of 5, which means the current for the same power has to be stepped down by a factor of 5. So this current works out to be 800 milliamps. What is the voltage loss in the transmission line? Well, the power loss is equal to I squared times R. The current being 0.8 amps, and we've got a resistance of 4T. So let's do that. So we've got 25.6 watts is lost, and that is due to a voltage of 1,200, well, that's some voltage times the current, which is 0.8. So divide that 25, we get 32 volts. There's a number of ways we could work that out, but I've just done it one way. Okay, so there's 32 volt drop. Otherwise, we could do V equals IR. The current being 0.8 amps, and the resistance being 40, which is also equal to 32 volts. So there's a 32 volt drop across here. So what happens is we've got 1250 volts coming through. It would be much more if the current was higher. So that's why they use transformers to set the voltage up, and then they step it back down once it gets down to here. So 1250 volts, so I can tell you now that there's going to be a voltage drop of 1250 minus 32, so there's going to be 1,218 volts coming through here because there's some voltage loss. Okay, so which I guess comes from a power loss in the lines here. So what is the power loss in the transmission lines? Well, we'll just work that out. See above 25.6 watts. What is the power used by the drill? Well, the power used by the drill is the power after the power loss. So we've got 1,000 watts, and there's a power loss of 25.6. So it's 1,000 take away 25.6. Which is 974.4 watts. What is the voltage across the drill? Well, the power across the drill, and the current, there's no current loss. There's a voltage drop. We can't use the 1,250. The power is equal to 974.4 is equal to the voltage, which is 218 from memory, times the, oh look, we've just worked it out before, haven't we? So I've actually, in doing it a different way up here, actually worked out the answers to all of those anyway. So the voltage across the drill, we worked out to be, due to this power loss, we worked out to be 1,200, okay, so 1,218 volts. But then that 1,218 volts is stepped down again. So 1,218.5 is 243.6 volts. So we've got 243.6 volts. Yeah, let's do it. That's how many volts is across the drill. Okie dokie. Times that by 4. If we were to do that, 240, and just to test out, when the current step back up at 4 amps, times that by 4, that gives us our 974.4 watts. So, sorry, I got a bit muddled up there. Shouldn't really try to do these so quick. Okay, let's have a look at the next question. Total resistance of the circuit is 50 ohms. What is the current flowing? Now, this one gets a little bit trickier because we know it's equal to 50. So therefore, we've got this 25 ohm resistor in series with this. So therefore, we know that R, forget about the 25 for a moment, this R plus 1 over 10 plus 1 over 30 is going to be to the power negative 1 is equal to 25. So let's go ahead and so therefore 25 take away this 1 over 10 power negative 1. Let's do that. 25 take 10 over 30. 17.5 ohms I've got here. 17.5 ohms. 1 over 10, 1 over 30, power negative 7.5, so 25 minus 7.5. Yeah, that's right. So 17.5 ohms. What is the current through the 25 ohm resistor? So that's basically, we just want to know what the total current is. So let's work out what the total resistance is. We're doing total that equals 50. So therefore, the current is equal to the voltage, which is 12. 0.24 amps. So we know that the current in is going to be the current out, so the current coming through the 25 ohm resistor is the total current, which is 0.24 amps. What is the potential difference across the 25 ohm resistor? Well, we know the current of the resistance is, so that's pretty easy. The voltage of the 25 ohm resistor, current of the resistance, which is equal to 0.24 times 25, which is equal to 6 volts. So we know that there's going to be across there, so there's going to be some voltage drop across here, and they're going to be add up to a total of 12. These two, 1 and 2, the voltage drop, those two added together are going to be the remaining 6 volts. Calculate the value of R. Well, look, I just did that before, haven't I? So I've done that before. The value of R, see above, is 17 ohms. See, by showing clear working, you can actually do the answers to a number of these questions in almost in one go. Calculate the power rating of the battery. Okay, so the power rating is V times I. V 12. Just 2.88 watts. Variable resistor has a range from 0 to 400 ohms. So that means that the resistance of this section here is going to go from anywhere from 0 to 400 ohms. And then as this resistance changes, it's going to affect the current in the circuit and hence the voltage drop at this point here. when the variable resistor is set to 0, what is the value of V out? Well, this is a voltage divider, a common voltage problem. So the current, let's work out the current is going to be equal to, the current is going to be equal to 120 divided by 225, which is equal to 120 divided by 225 is 0.533 amps. So the voltage across the 75 resistor is going to be equal to this 0.5333 times 75, which is equal to 40 volts. So there's going to be a 40 volt drop across. And look, that's you could have done this without doing any calculations, because the voltage drop is proportional to the resistance in this series circuit. So given that the resistance is twice the size, or sorry, half of this, then we know that the voltage is going to be split 80-40. To have a voltage out of 1.5 volts, what must the value of the variable resistor be? Now that's where some of you are going to struggle if you don't know how to do your setting out properly. So voltage out though is equal to 1.5, which is equal to the current, which we don't know, the resistance, which is 75. Equal to 0.5, 0.02. And we know that the current is through there, so the total current is that. So what value must the variable resistor be? Well, I is equal to V over R. V over R. 120 over the resistance. Now, we know that there's a 75 ohm resistor, and we've got a 150, and they're all in series. So we've got 75 plus 150 plus our variable resistor, we'll call R, is equal to this. So we just need to rearrange, and let's do that now. This is where some of you with maths will have some issues. So let's go ahead and do that. So we've got 225 plus R. So 225 plus R outside of 0.02 is equal to 120. So let's rearrange. We need to solve for R. So therefore R is equal to, running out of room here, R is equal to 120 minus 0.02 times 225 divided by 0.02. Times 225 divided by 0.02. So, what have I done there? Okay, so let's try that again. 0.02 is equal to V, which is 120, over R, which is 225 plus 225 times 0.02 plus 0.02 is equal to 120. So 120 take 225 times 0.02, 4.5, take away 4.5 divided by 0.02. Don't know what I've done there. So 0 to 400 ohms. I've got 5,775 ohms. And which clearly can't be right, so I've done something wrong in here. So the current is equal to the voltage, which is 120. Okay, so we've got 1.5 volts. Is equal to the current, which is we don't know, is equal to 1.5 divided by 6. Yeah, that's right. Alright, let's leave that one for the time being. Trying to get this video finished. I'll come back to it though. A UPod MP3 player runs at 175 milliamps and is powered by a 3.7 volt battery. The battery has a capacity of 1850 milliamp hours. How many joules of energy does the UPod use? So energy equals power times time. Our power is the voltage times the current, so that's 3.7 times 175 by 10 to the minus 3 times 180 seconds. Put that in your calculators. Got 116.55 joules. 116.5 joules will be enough. How many electrons move through the UPod while it is playing music for 3 minutes? Well, the charge, we need to find what the charge is. So the charge is 175 milliamps times 180 seconds, which is equal to 31.5 coulombs. Now, for each coulomb of charge, there is this many electrons. Oh, actually, 1 divided by 6.25 by 10 to the 18 electrons. So, therefore, the number of electrons is equal to the number of coulombs plus the amount of electrons per coulomb charge. So we've got 31.5 times what we have up here, which is equal to 1.97 by 10 to the 20 electrons. Okie dokie. How long could the UPod play continuous music for? Well, it has a battery has a capacity of 1850 milliamp hours. So we've got, that's going to be equal to 10.57 hours to be fine. So 1850 milliamp hours, well, it's going to be 175, that means that it can handle 1850 milliamps for an hour. So given that it works out roughly to 10.57 hours. Have a look. I think that this this question is fairly easy. I think you should be able to do that. So I'm going to skip that one. Let's skip that one too. Okay, let's do this question 13. A farmer Giles wishes to connect a 12-volt water pump, produces 240 volts. His water pump is 2.5 kilometres away from a generator. If he has a transformer with a primary coil of 700 turns, how many turns are we needed on the secondary coil? So the ratio between the number of turns of 1 and the number of turns of 2 is going to be equal to, now it's going to step the voltage up. He's going to step the voltage up. So therefore, it's going to be so let's have a look at what we know. The number of turns in the primary coil is equal to 700. The number of coils in the secondary coil is equal to, we don't know that. The voltage, the 12-volt water pump. Okay, so the generator is generating is equal to 240 volts. And V2 is equal to 12. So what he's doing is he wants to step the voltage we've got 240 volts going through here, and then it's stepped down, the voltage is stepped down to 12. So let's plug in what we know. So we've got 700 over N2 is equal to 212 over 240. V1 over V2. 240 over 12. So therefore, N2, 240 over 12 is 20. 700 divided by 20 is, so therefore the number of coils is going to be 700 divided by 20, which is equal to 35. So what he's done is that we have 240 volts coming through. He then wants to step that down to 12. So what he does is he has a transformer which has 700 coils. This is 700 coils, and the secondary coil for the transformer has 35 coils. Now that ratio of 700 to 35 is 20 to 1. So that's going to step the voltage down by a factor of 20. So that's how a transformer works. So what the number of coils that he has is 35. Without the transformer, the current would be too big and the water pump would quickly burn out. What would be the current through the wires without the transformer in place? Well, we know that it's a 15 kilowatt transformer, so 15,000 is equal to 240 times the current. So that's quite a big current, isn't it? Which is equal to, wow, 2.5 amps. So what happens is that when that current, the voltage is stepped down by a factor of, so if he doesn't step that voltage down, then the current is going to be 62.5 amps. Okay. Farmer Giles wants to replace his transformer at point B. Mr. Giles says that to save electricity, he should place it at point A. Explain why. Well, it will make sense because what happens is there's going to be a power loss. So what he needs to do is he needs to actually step, he has the voltage down here, B1, he needs to step that up, which then reduces the current, and then since the current or the power loss is equal to I squared R, this severely reduces the loss of power in the line. Now you can't really do much about reducing the resistance because the resistance, is pretty much due to the wire, and there's not much you can do. You might be able to, have a small reduction in resistance, but considering that the power loss is proportional to I squared, then it makes sense to reduce the current by stepping up the voltage. Resistance in the connecting wires between A and B is 1.2 ohms. If the transformer is placed at B, calculate the power loss. So power loss is equal to I squared R, which is equal to 1.2 ohms times the current. Have we worked out what the current is? Yes, 62.5 amps. And that's squared too, by the way. So 62.5 squared, 1.2. So with him not doing anything until the electricity is transmitted through the wires, he's actually going to lose 4,687 watts of power from an initial 15,000 watts. So he's lost, about 33% of his power there. Okay, this is still going? No, that's the next one. All right, let's have a look at the next question. Resistor was tested under a DC current. The IV profile of the resistor is shown. Second resistor was added in series. The second resistor has a resistance of 10 ohms. On the graph, draw the IV profile of both resistors together. I think I'm going to do this in part 2 of the video. I think I'll stop there. It's already gone for 45 minutes, so I'm going to stop there and I'm going to go address this question in part 2.